Okay, today we'll continue with group actions. So let G be a group and S be a set on which G acts. Let G be a group and S be a G set. So it's a set S on which G acts, and you have an action from G cross S to S that sends a pair GS G star S. Then there exists a homomorphism rho from G to a symmetry group on S that sends little g to lambda G, where lambda G is the function from S to S that sends little s to G star S. We saw that this is a bijection. And the kernel of rho is the intersection of all, let's say X and S. It's the intersection of all the stable answers. Okay, we saw this last time, right? Remember? Yeah? This is how we finished last time, yeah? Okay, now let's study an application of that. Let G be a group. This is called people call it Coset representation. Let G be a group. And H a subgroup of G of finite index n. Okay, so I have a group, not necessarily finite. The group is not necessarily finite, but I have a subgroup of finite index, sync of Z and NZ, basically. Z is infinite, but NZ in Z has index n, has finite index. Great. G acts on the space of left cosets G mod H. So just XH as X is in G by the following. This is obviously an action. Well, G. I take a G and G and a coset XH, and it sends me back the coset GXH. I have a left coset XH. When I multiply by G on the left, I get a left coset. So really, this is an action from G on G mod H, and you get back an element of G mod H. Now, star is a group action. I can show it. I mean, what is this? EG star XH is just EG XH, which is just XH. So here, let X be G. And then G1 star XH. This is just G1 star G2 XH. And this is just G1 G2 XH. You can show this is easily equal to XH, which is just G1 G2 star XH. Okay, let X be G, G1, G2. Okay, so this is a group action. This action induces a homomorphism homomorphism row from G, the symmetry group on G mod H, the set of bijections from G mod H to itself. Well, G mod H has n elements. Let's say by labeling those elements 1 up to n, this symmetric group of G mod H, you can identify it with Sn. Isomorphic to Sn. Just label the elements 1, 2, 3 up to n. And you can identify the symmetric group on G mod H by Sn. Okay, now what is the kernel of rho? What is the kernel of rho? The kernel of rho is the intersection of all the stabilizers. Okay? How do I find the stabilizers? Let's just look at this. So we need to find stab S for all S in G mod H. Let's do this. So any S in G mod H basically is a left coset. So it's of the form XH where X is in G. So I claim that stab XH is, let's see if I get this right. This is just X stab H X inverse. Or you know what, let's not do this here. This is just XH X inverse. Claim. Let X be G. Then stab X H is X H X inverse. Let's prove this. So G belongs to stab XH if and only if G XH is equal to XH, if and only if X inverse G XH is equal to H. Right, now this is obvious here. This becomes if and only if X inverse Gx belongs to H, and then if and only if G belongs multiplied by H on the left and on the right, X on the left to cancel this one, and X inverse on the right to cancel this one. Okay? So G belongs to stab XH if and only if G belongs to XH X inverse. This shows it. Okay? Agree? You just have to be comfortable with the definition of a stabilizer and the definition of an orbit and see what the action is. The definition of a stabilizer and the definition of the action. And in this case, you just have to be comfortable with cosets. Okay? So basically, when G acts on XH means that G doesn't change XH, basically. Right? This is the stabilizer. Okay. Therefore, what is the kernel of rho? The kernel of rho will be the intersection of all of these, right? You see that? It's the intersection of all the stabilizers. So what are all the stabilizers? What is the stabilizer of XH? This is just XH X inverse. Hence, kernel of rho is the intersection as X is in G of XH X inverse. Oh, okay? So far so good? Yeah? Now, what are the properties of this? This is a normal subgroup, of course, but what is the index of kernel of rho? G modulo the kernel of rho. So, by the first isomorphism theorem, G modulo the kernel of rho is isomorphic, well, I mean, that's is isomorphic to rho of G, which is a subgroup of the symmetric group of G mod H, which is isomorphic to Sn. How many elements does the symmetric group of G mod H have? How many elements does Sn have? N factorial, right? So the order of G mod kernel of rho is finite. So G mod kernel of rho, which is equal to the order of rho G, is finite because it's a subgroup of the symmetric group on n letters and divides n factorial. So if you have a subgroup of finite index, then you can construct a normal subgroup of finite index that is contained in the subgroup. Kernel of rho is contained, well, which is equal to the intersection as x is in G of x, h, x inverse, is contained. If you put in 1 for x, what do you get?
What do you mean 1?
Identity, sorry. What do you get? You get h. The kernel of rho is contained in h. H has index n. And you know that kernel of h, the kernel of rho, has index dividing n factorial. Okay? Yeah.
But isn't the subset saying that it should be the opposite because you're specifically choosing EG? Because
No.
X is not
So
specified.
the intersection of all of these, it's EG, H, X, and EG inverse, right? Pick another one. Pick another element that is not an H, right?
Yes, and
So this is a subset of that. This is a subgroup of this.
why?
This is the intersection of X, H, X inverse as X is in G, right? If you fix a value of X, then this intersection will be here.
Why?
Let Y belong to this intersection, right?
Yes.
Then Y belongs to all X, H, X inverse.
Yes.
Maybe if you
In
draw,
particular, if you plug in, if you put in X equal EG, then Y will belong to H. Okay?
Okay. Yes.
Yeah?
I was gonna say, like, I think a better way to explain that would have been to like draw each intersection, like you choose like
Yeah, I mean, you could do that, but the intersection could be crazy, right?
yeah.
Okay? I mean, let's think of it abstractly. Is that clear? That the intersection of these is a subset of this one? If you have the intersection of X, right, like, yeah, that's clear, right?
Because the intersection only reduces the amount, and so since there is that,
Sure.
it will just be at most H.
Exactly. Exactly. So kernel of rho is a subgroup of H. Kernel of rho is a subgroup of H. And the index of kernel of rho is finite, even if G is infinite. Which is pretty cool, I guess. Okay? Great. Now, let's give an application of that. So, proposition, if G is a group, and H a subgroup of G, then there exists a normal subgroup N of G such that N is contained in H, a normal subgroup, and GH has index N and finite, and you have a normal subgroup of G such that n is contained in H, and G, the index of G of n, divides n factorial. Okay, in particular, the index is finite. Pretty cool. This action you should be very comfortable with. Okay? This is called the coset representation, the left coset representation. Did I write this word? Left coset representation? Yeah. Great. Okay. Now, how to apply that? We'll apply this. I mean, there are many ways to do this thing, but let's use the coset representation proposition. Let G be a finite group. And H a subgroup of G of index P, where P is the smallest prime divisor of G. Then H is a normal subgroup of G, which is pretty cool. So if you have a group, so say you have a group of order, I don't know, 27. What's the smallest prime divisor of 27? 3. And you have a subgroup of index 3, then this subgroup is normal. This generalizes the thing what we did with subgroups of index 2, right? If you have a subgroup of index 2, this means that the group, and the group is finite, say, this means that 2 divides the order of the group, and 2 will be the smallest prime divisor. Okay, so this generalizes what we have done before, and we'll prove this using the coset representation. Now, if I want to show that a subgroup is normal, what can I do? If I manage to show it's the kernel of a homomorphism, am I not done? The kernel is a normal subgroup. So if I show that the subgroup is the kernel of a homomorphism, then I'm done.
So when is the kernel of a homomorphism?
Great. So let's do that. Let's prove it. I mean, I'll write down a small sketch of the proof because I think it's homework. So I'll write a small sketch and then you have to fill the details in. Yeah.
Can you just quickly explain again why the kernel is a normal subgroup?
Just write down the property. So if X belongs to the kernel of homomorphism phi, take Gx G inverse, right? Apply G to both sides. Apply phi here. This is just phi Gx G inverse. This is just phi of G, phi of X, phi of G inverse. This will be the identity. Okay? G and G, X is the identity, phi of X is the identity. Phi of G and phi of G inverse will cancel out, you get the identity in H. If you have a group homomorphism from G to H. Okay?
But how does that show it's normal?
It's a subgroup first of all. And Gx G inverse belongs to a kernel of phi for every X in kernel of phi and every G in G. Okay? Yeah, normal subgroup. G belongs to G, H belongs to H, GH G inverse belongs to H.
Okay.
Okay? And here you just show that. Then H is a normal subgroup of G. Let's prove this. I mean outline, sketch basically. Let N be the kernel of the coset representation of G mod H. Or you know what, let's be more clear. Of the action G on G1H. Now, we know that N is a subgroup of H, and the index of N divides B factorial. Right? By the previous theorem. Look at the previous theorem. Look at the previous theorem. We know that the coset, the kernel of this is G modulo the kernel is a subgroup, is isomorphic to a subgroup of Sn. Yeah? Are we good? G modulo the kernel is isomorphic to a subgroup of Sn. So G modulo the kernel has size dividing n factorial. Now, what do I know about G mod n? The index of n, the index of n in G. G mod n also divides G. Right? This is obvious because the order of G is G, the index of n, times the order of. Hence, G mod, the index of G and n divides the GCD of G and B factorial. Right? If it divides this one, and divides this one, then it divides their GCD. Now, what is the GCD of the order of G and P factorial? If P is the smallest prime divisor. Yep, it's P, right? You guys see that? If P is the smallest prime divisor of G, then GCD of G and P factorial is what? P, right? You guys see that? Try to write it down. Since P is the smallest prime divisor of G, then GCD of what? Of G and P factorial is just P. Yeah.
It's the smallest, but how does that say that the P factorial does not include other divisors of G?
Sure. Let Q be a prime divisor of P factorial. Very good question. Let Q be a prime divisor of P factorial. So P factorial is P times P minus 1 times P minus 2 times 1. Right? Yeah? If Q is a prime divisor of P factorial, then Q must divide one of these. Now, P is the smallest common divisor. So none of the prime factors of P factorial is a prime factor of G. Because all the prime factors of P factorial, since P is prime.
Yeah, but we're looking for the greatest common divisor between them.
Yeah.
It's possible that those smaller ones are also divisors of G, no?
No, P is the smallest divisor of G.
The smallest prime one.
Yeah, but if the smallest prime divisor, then the smallest divisor is bigger than 1. Right? What is the smallest prime divisor of 25?
5.
What is the smallest divisor of 25 that is bigger than 1?
5.
Right? So the smallest prime divisor is the smallest divisor.
Because there cannot be any composite number underneath. Else
Exactly.
you can take a prime
Exactly.
from underneath.
Exactly.
Okay.
Exactly. Is
Yeah.
that what you wanted to say? Okay, thank you. Hence, the index of G and N divides P. The index of N in G divides P. So Gn is 1, or Gn is P. Now, why can I rule out the fact that G, the index of N in G is 1? Anyone can help? What does it mean that the index of n and g is 1?
They're the same.
They're the same, exactly. It means n is equal to g. If g n is 1, then n is equal to g. But we know that n is a subset of h, which is a proper subset of g. H is different than g. Okay, so far so good. If h is different than g, and n is a subset of h, then n can't be equal to g. Well, this leaves us with the fact that g index n is p. Hence, contradiction here. You got a right contradiction. Now, if g index n is p, if g index n is p, and well, n is contained in h is contained in g. So I know that the index of g and n, well, I mean, let's pose more generally, but this is this. I'm working with finite groups here, so this doesn't matter. So I can write that the index of g and n is the product of the index of h, the index of n and g is equal to the index of h and g times the index of n and h. All of these are subgroup of each other. Now, what is the index of g and n and g? Oh man. What is this one here? P. What is this one here? By assumption, h is the index of, has index p. So what is the index of n and h? P. So this has 1. So h, n is 1. What does it mean? N is a subgroup of h, and the index of n and h is 1. What does it mean?
They're the same.
N is equal to h. So h is equal to n. If h is equal to the kernel of a homomorphism, then h is a normal subgroup of g. N is a normal subgroup of g. N is normal in g since it's the kernel of a homomorphism. And h is equal to n. So h is normal. That's a very nice argument. There are other arguments. I think yesterday in office hours I did another argument. I think it looks it is a bit simpler. Was it simpler for those who? Was it simpler? Yeah, I mean, what you can do here. I mean, yeah, I mean, okay, let's that's not anyways. Okay. Are we good?
Yeah. This is hard to think of.
Yeah, no, it's not easy. This stuff is not easy.
Like, how could you like just guess randomly to make that normal subgroup n and then equate it eventually?
Exactly. So if you want to show something is normal, you can. There are many ways to do it. One of these ways is to express it as the kernel of a homomorphism. This is yeah. If you express it as the kernel, you win. Now there are other ways, but yeah. So it's you can show left cosets are right coset. You can I mean you can. Yeah, it's usually this is given as a homework problem. I mean, I gave it as a homework problem.
You did.
And I gave the answer. So, yeah.
It's on the bonus.
Yeah.
If we didn't use like this kernel argument.
Yeah. You want to show another argument?
Well, would it be like the same idea that we use for like index 2, which is like we have the smallest p and then there's no room for other ones.
Something. Well, okay. I'll give you a hint. Maybe if we can do it the last 5 minutes. Okay, I can give you a hint. I mean, the idea is that to let h act on g mod h, right, and show that all the orbits have size 1. Okay, this is you do it by very silly number theoretic arguments. Okay, and then you write down what orbit of size 1 means. It comes out clear that H should be normal. This is very good way. Okay, now let's apply. Are we good here? It's difficult, but you should get used to it. Okay? Please study during the weekend. Please study. Okay? Study group actions. I know you haven't been worrying a lot about this, but in the weekend, please take the time, 3-4 hours to look over the group action material. Great. Now let's do let's do one more application actually, or maybe let me give another definition, and I'll do one more application. Definition. Let G be a group, and S be a GC. We say that G acts transitively on S, or the action is transitive, or the action of G on S is transitive, if well, I'm not to write this down. Well, if S is the only orbit, so basically S transitively, G acts transitively on S if there is only one orbit, which is S. Basically, you can get from one element to another element by letting G act. Okay? Now, proposition. Let G act, well, G acts transitively on S. Let S be a finite set with n elements. Then G acts transitively on S if and only if G has a subgroup of index n. Another proposition. I'll leave this as an exercise. I think I'll put it on the homework for you today. I mean, this is not bad, right?
The what?
This proposition is not bad. If G acts transitively on S, take the stabilizer of an element. By the orbit stabilizer, the stabilizer has index n. Now, conversely, if G has a subgroup of index n, you can show that the action of G on G mod H is transitive. Okay? I told you how to do it. Okay? What is now next proposition, which is also more or less obvious. Let me write a more definition. Now a transitive subgroup on Sn and transitive subgroup. Oh man. A subgroup of Sn. Is said to be transitive ig in Sn, for all ig in 1 up to n, there exists sigma in H such that sigma I is equal to G. Really, this is related to this definition by just letting Sn act on the set 1, 2, 3 up to n. By taking a sigma and an I, and sigma star I is sigma I. Okay, for example, H is equal to 1, 2 is not a transitive subgroup of S3. Right? Can you go from 3 to 2 in an element with an element from H?
No.
No. But H, well, let's not use H. Well, let's use H prime. 1, 1 to 3, 1, 3, 2 is a transitive subgroup of S3. Right? You can go from 1 to any other element, and that's it.
Wait.
Can you go from 1 to 3 on this, can you find an element in H that takes 1 to 3?
This
Yeah.
the one?
Can you find an element that takes 1 to 2? So you can find an element that takes 3 to 2, right? Okay. Okay, now armed with these definition, we will, well, we will start a new, more or less a new section in group action. These are called P groups. Okay, we did some basics in P groups. And group actions are very useful with P groups. Okay, so please study this stuff, repeat it, rewrite them. It's these are not easy concepts, and only like when you practice them, you will be able to, you will be able to get better at those things. Okay, I'll post a lot of exercises of concerning group actions. Okay, great. How much time do I have left?
13 minutes.
13 minutes. Okay. Now a new section would be P groups. A finite group, so let P be a prime. This stuff you have seen before, okay? We'll just combine everything and do one more theorem, and then maybe end this lecture. Okay? How do you find this group action stuff? Is it tough?
Like, I understand what you say, but I don't understand how to work with it.
Yeah. Yeah. I think in the next homework I'll make you prove Fermat's-Little theorem with group actions. So you can prove Fermat's-Little theorem with group actions. Which is, yeah, we'll see how to do that. Very, very nice proof. Just wow, when you look at it, you're like, wow, this is very nice. At least this is how I felt. But yeah. Let P be a prime, a finite group G is said to be a P group. Now I'll exclude one from the definition of a P group. Like the trivial group, I will not assume it's a P group. Okay? Now some textbooks assume it, some don't. But I've seen like both, but it doesn't matter. It's not the definition that matters. It's more the it's more what we do with them. So it's said to be a P group if G is equal P to the K for some K in N. try to, yeah, so usually like k cannot assume to be 0, but some do assume it. Not a big deal. Okay, it's not a big issue. Okay, what's the first theorem we saw on centers of P group?
It
They
has
are?
to be also multiple of P.
Has to be bigger than 1 and in fact a multiple of P, right? You remember this? One. If G is a finite P group, we have seen that ZG has size bigger or equal to P, right? Remember this? Homework 4? Remember that?
Yeah.
How did we prove this? We took the class equation, well, we took the conjugacy classes of G, right? When you let G act on G by conjugation, now that we know this, and you look at the singleton orbits and the non-singleton orbits, the set of singleton orbits will just be the center, and the set of non-singleton orbits, I think I used this, where xk, xn are representatives of non-singleton orbits, of non-singleton conjugacy classes. And we saw that, okay, this is how we proved it. Okay, see homework 4. Now we also saw that a group of order p squared is abelian. This is in this homework. Now let's prove more stuff about P groups. Yeah, this is in this homework, right?
This
A group-
homework.
A group of order P squared is abelian, no? The one due on, the one due today.
On Monday. It's,
The one due today, right? There is one due today.
but
And this is the question.
it's Monday.
What?
Come to homework 6.
Oh, 6.
Yeah, the one that is due to-
7.
Yeah, no, 7 is not, no, but this one is on the question list, right?
Yeah.
I don't
To my
remember
memory.
that.
Yeah, yeah, yeah.
I don't
Yeah.
remember that.
Okay,
I do not remember that.
okay,
I don't
so
think so.
is it on? I'm pretty sure it's on the question list.
It was there.
Yes.
Would you have one question that for like how to find the cardinality of G? I never understood why ZG wasn't trivial. I never figured that out.
Oh, okay. Thank you. So these conjugacy classes, this is the size of the conjugacy class, right? And you know that the size of a conjugacy class must divide the order of G, which is P to the K. So it must be a power of P. Agree? Since P is prime. Now, since this conjugacy class is not of size 1, then this, so, you know, it's either 1p, p squared, and so on. This one. Now, you know that this orbit, or this conjugacy class, doesn't have size 1, because representative of non-singleton conjugacy class. So it doesn't have size 1. Agree? So all of these is a sum of multiples of P. Agree? G is a multiple of P as well, because it's P to the K for K bigger or equal to 1. Agree?
So ZG has to be the rest of the multiples?
Exactly. So this is a multiple of P, this is a multiple of P, so this must be a multiple of P. Now you have, so ZG is either 0, P, 2P, and so on. Z, P squared, and so on. But can ZG be 0? No, because you have the identity inside. Is that clear? Yeah.
Is ZG a billion?
Yes, ZG is a billion. Yeah.
ever show that?
No, not necessarily, but ZG is a billion. Yeah, that's right.
Why?
ZG, just write down the definition, you get it's a billion. Yes?
For the second one, like if G is like B squared, then it's a billion, it's only an if.
It's only?
Is it if, or is it if? and-
So ZG is equal to G if and only if G is a billion.
No, I mean the second one.
A group of order P squared is a billion.
Yeah,
So if G has order P squared, then G is a billion.
yeah, but it only goes one way.
So if G is a billion, then G has order P. What do you mean?
Yeah, like
You
can't
mean for
say-
all groups,
Like you can't say if G is a billion.
then G has order P squared?
Yeah.
No. You can find a group of order P cubed, for example, that is not a billion. Very good question.
That's what I think true also.
You can find a group of order, not all P groups are a billion, if that's what you're asking. Not all P groups are a billion, yeah. Okay, now, we'll do that small proof by induction.